Okay, Chemistry 3101. What I asked you to do for last class was to cover these problems. So this is question 5.39 from the textbook. I didn't write it down here, but this is question 5.39 from the 4th edition of Klein. So it's 5.39 A, B, C, and E. So with A, if we start with A, okay, we have a chiral center, which is right here where I'm putting this blue dot, okay? So there's our chiral center. We can tell it's a chiral center. Why? Because it's attached to 4 different groups, right? We've got a hydroxyl, an ethyl, a methyl, and then we've got all this spinach over here, right? So those are clearly 4 different groups. Now, the lowest priority group of all of these, okay, if you haven't picked up on it, when we go, when we prioritize straight chains, the longer they are, the higher priority they have. So what does that mean? So that means that an ethyl group, so an ethyl group would take priority over a methyl group, and a propyl group would take priority over an ethyl, right, and a butyl, so on and so forth. So if it's just a straight chain, that means the ethyl is going to have a higher priority than methyl, okay? Then you can see that this group is going to have a higher priority than the ethyl or the methyl, right? Because when we get to the second carbon, it's attached to oxygens, whereas the second carbon in ethyl is only attached to hydrogens. And so if we prioritize our groups, we have 1 for the hydroxyl, 2 for this group over here, 3 and 4. So our methyl is the lowest priority group, okay? So there's kind of 2 ways you could approach this problem, because the lowest priority group is not in the back, okay? And it's not in the front, it's in the plane of the page. One way would be to pretend you're looking at the molecule like this, okay? So if this is your eyeball, pretend you're looking down this bond like this from here to here, because that way the methyl group would be in the back. And then what you would see is you would have the hydroxyl coming up here, you'd have the ethyl over here, and then you would have the ketone group coming down here, right? And then you would just do 1, 2, 3 like that. And when you go like this, it's going counterclockwise. And so this is an S compound. So this is an S stereocenter. That's one way of doing it. But there is another way if you don't follow me on that, okay? There is another way to do it. So if you remember the rules that were in the slides, what it said was, if you switch 2 groups, so if you switch any 2 groups, let's say you switch, I don't know, these 2 groups, or let's say you switch these 2 groups, what you do is you change R to S or S to R. So what we could do is we could swap the methyl and the hydroxyl, and then we just read it the way it is, and then whatever it is, we reverse it. So if we get R, it would be S. If we get S, it would be R. So if you don't follow me, let me demonstrate it for you. So I'm just going to redraw the compound. I'll just redraw the compound like this. So here's my carbonyl group. I have my ethyl here. And what I'm going to do is I'm going to swap the hydroxyl and the methyl. So that way, the methyl will be in the back. Okay, it's the lowest priority group. And then the hydroxyl group is going to be over here. Okay, so now what we're going to do is we're going to prioritize again. We have 1, 2, 3, and 4. The lowest priority group is in the back now, but again, we swapped 2 groups. So we're going to go from 1 to 2 to 3, which is clockwise. So if it's clockwise, it would be R, but we know we switch it. So that again tells us that this is an S compound. So no matter which way you do it, you end up, can you guys still see the slides? Sorry about that. You end up with an S compound. Okay, cool, thanks. Sorry about that. All right, so either way, it's an S compound. And there you go. So I know I'm recording this right now, but I'll just tell you guys, I don't know what happened, but for some reason, I've gotten about 10 calls this morning from telemarketers. So, and I don't know why. So that was nobody I know. It's probably a telemarketer. Anyhow, so there we go. So there's the first one. I think the next one is a little less challenging. This amine here. Let's put in the proton, the hydrogen that's not drawn at the chiral center. So we'll stick it in here like this, okay? And so our lowest priority group is coming out towards us. So whatever we get, R, we'll flip it to S, or S, we'll flip it to R. So nitrogen obviously has the highest atomic number. Then I told you an ethyl is going to take precedence over a methyl, and then the hydrogen is going to be the last. And so we go from 1 to 2 to 3. This is clockwise. So clockwise would mean that it is R, but remember we reverse it since the proton is coming out, in front. And so this would be an S compound as well. Give me a thumbs up if you're with me on that one. And we have a second S compound, okay? And don't hesitate to stop me if you have a question. Okay, all right. So there we go with that one. All right, let's try this one, which is a little more involved, I think. So we have our chiral center. We have our hydrogen going in the back. We like that, right? Because that's the lowest priority group. Chlorine is number 1. Then here we have a carbon in blue, and here, sorry, in red, and here I'll put a carbon in blue. So let's list what these are attached to. Now remember, when you make the list of 3 atoms that it's attached to, it's going away from the chiral center. So the carbon in red is attached to this carbon and then 2 hydrogens. Okay, so I'm going to list those in order of their atomic number. So this carbon is attached to carbon, hydrogen, and hydrogen. If we go to the carbon in blue and we do the same thing, we get carbon, hydrogen, and hydrogen. So we still don't have a tiebreaker. If I go to this carbon, it's attached to carbon, hydrogen, and hydrogen, right? This carbon and the 2 hydrogens that are on it, okay? So let's go over here. Oops. Let's go here to this one. And this carbon that's in green is attached to carbon, carbon, hydrogen, right? Carbon, carbon, and then a hydrogen here. And so you can see where the tiebreaker is. The tiebreaker is right here. And so that means that the sec-butyl group is going to take, or sorry, the isobutyl group is going to take priority over all this group here. So we have 1, and then this carbon, this is going to be 2, this will be 3, and then we have 4. So we read it the way it's written. So we go 1, 2, 3, which is clockwise. Therefore, if we're going clockwise and the hydrogen is in the back, this must be an R compound. So we've got S for the first 2, and then we've got R for the third one. Well, let's do the last one. So this is 5.39E. Again, our lowest priority group is coming out towards us. Our highest priority group, the fluorine, is in the back. So we're going to reverse whatever we get. This carbon in blue is attached to carbon, carbon, hydrogen. This carbon in red is attached to carbon, hydrogen, hydrogen, like that. So you can see the tiebreaker is this one here, the carbon in the middle, okay? So now we have 1, 2, 3, like this. So we're going to go, let's get my green pen. So we're going to go 1, 2, 3, which is counterclockwise, right? Counterclockwise is S, but we're going to reverse it. And so this would be an S compound, or sorry, an R compound as well. So there you go. Everybody with me on the Kahn-Ingold pre-log rules? Does that help a little bit? I'm sure you all took the time to practice these. All right, cool. There we go. So now we've figured out the Kahn-Ingold pre-log rules a little bit. So again, designating R versus S. Okay, this has got a name. It's called the Kahn-Ingold pre-log rules. Okay, so there you go. So, so in B, yes, it's S because if the lowest priority group comes out towards you, you have to reverse the designation. All right, the way the rules work is the lowest priority group has to be behind you. Okay, it has to be going away from you, but if it's coming in front, you just reverse it. R becomes S, and in this case, or S becomes R. So in this case, we read it as if it was R, so it becomes S. Does that help? Okay, cool, great, awesome. So with that in mind, let us celebrate some more chapter 5 by going through this. So we went through all the Kahn-Ingold pre-log rules last class. So again, you know, the best way to master it is just to practice it over and over and over. And like I told you last class, students usually get very good at assigning R and S, but these are the rules here, okay? Those are the rules in a nutshell. So they are posted in the slides, and of course they're in the textbook. And so let's talk a little bit about what's called optical activity. Because when we're talking about things like melting points and boiling points, where do they come from, right? They come from intermolecular forces between molecules. And if you think about the way molecules pack together, just like chairs can stack together, if I have enantiomers, so meaning if I have this molecule R carbone, S carbone, remember these are enantiomers because there's one stereocenter, and you can see that the wedge in R carbone is flipped to a dash. In S carbone, you see that enantiomers have the exact same melting points and the exact same boiling points. The reason why is because they're going to pack together in an identical fashion. So it's going to take the exact same amount of energy to break those intermolecular forces between the molecules, right? The melting points, boiling points, infrared, mass spectra, proton, carbon NMR that we're going to look at later on, all of these things will be identical. And so if you're wondering, well, how do you differentiate between them? Okay, it's a great question, and we're going to try to answer that right now. So enantiomers only differ in two ways. One, how they interact with other chiral compounds, and that's something that we don't really unpack in this class. But if you imagine an R compound is going to react with another R compound differently than an S compound would react with an R compound, that's what that means, okay? But what we're going to investigate in this class is what's called their optical activity. It's how they behave or how they affect what's called plane polarized light. Okay, so plane polarized light. And light is something that we've talked about recently. We did a whole chapter where we talked about light when we were talking about infrared spectroscopy. So we talked about how light is an electromagnetic wave that has two perpendicular oscillating planes, an electric one and a magnetic one. And if you think about light when it travels from a light source, okay, what happens is that the light travels towards its source, but then you have the waves of light traveling in all directions perpendicular to the direction of travel, okay? So what that means is when we shine light, so let's imagine we have a light bulb here, okay? So here's my light bulb, okay? The light goes out in all directions, okay? It goes out in all directions. And what you can do is you can pass light through what's called a polarizing filter, okay? Now, if you have an expensive pair of sunglasses, or you can even buy inexpensive polarized sunglasses from Amazon or something. But if you have polarized sunglasses, sometimes they'll come with a filter that is attached to the sunglasses when they're hanging up in the store, and you can actually test the polarization of the lens. But the idea behind a polarizing lens is that you have the light oscillating in all of these planes, an infinite number of planes. Then you pass it through the filter. Okay, this is a plane polarizing filter. And then you only get the light going in one direction, right? So this is just one plane of light. You see how you have all these arrows going in all these different directions. You shine it through the filter, and we get what's called plane polarized light, okay? So it says when you have plane polarized light, after it goes through the filter, you have a second filter here, okay? And if the second filter is aligned with the first filter, you're going to see the light with your eyeball, okay? Light's going to pass through. But if you rotate the other one 90 degrees, so you can see it's been rotated 90 degrees here, then it blocks out the light. Okay, so before you're like, okay, well, what's the whole purpose of this? Let me unpack it a little bit more, and you'll be able to figure out what's going on. So it says, when plane polarized light is passed through a sample of a chiral compound. Okay, so here's where it gets interesting. So now if we take a compound that is an S compound or an R compound, something that is chiral, okay, let me just highlight that. So a chiral, when we shine it through a chiral compound, what's going to happen is the light is going to rotate. So the plane polarized light will rotate. Okay, so let's talk about this again. Okay, I take my plane polarized light, okay, and I shine it through a solution of an organic compound that is chiral. And what it's going to do is it's going to cause the plane polarized light to rotate. So it says compounds that can rotate plane polarized light are called optically active. And it turns out that the good news for us as chemists is that only chiral compounds are optically active. So what that means is if you have a compound that has no chiral centers in it, there's no point in shining plane polarized light at it because it doesn't do anything. But if you have an R compound or an S compound, something that is chiral, and you shine plane polarized light at it, it turns out that the compound is going to rotate the light. Okay, so let me show you what that means. Okay, so here's our light source. Okay, and what we usually use is the D line of sodium. So this is the D line of sodium. If you remember from spectroscopy in General Chemistry 1, you talked about the hydrogen lamp and then the helium lamp and all that stuff. So this is just a sodium lamp is what we use. So the light is coming out in all directions, okay? Then we put it through the polarizer, okay, what I call the polarizing filter. It's the same thing. Now inside what's called the polarimeter tube, this is where you have a solution of a chiral compound. Okay, and the chiral compound is going to work its magic. You see the plane polarized light in one direction here, but you see the compound is rotating it. Okay, so the compound rotates it itself. And so what you do with the analyzer, meaning the filter on the other end, is you're the viewer, right? The observer is down here with your eyeball. You're looking at it, and you take your hand, okay? So you take your hand, and you're going to rotate this until you can see the maximum amount of light coming through. And then you're going to read the angle here, and that's going to tell you by how many degrees your chiral compound is rotating the plane polarized light. Now, at this point, hopefully you're connecting the dots and just saying, okay, great, whatever. I have a compound. I put a chiral compound. I put a solution of it in this tube. I shine the plane polarized light through it, and then the chiral compound is going to rotate the light, and I can measure the amount of rotation. You're absolutely right, okay, if that's what you're thinking. Now, here's the best part of all. If you have an S compound versus an R compound, so two compounds that are enantiomers, let's just say, and I'm just pulling a number out of the air, okay, it doesn't mean anything. Let's say your S compound rotates the plane polarized light positive 24 degrees. Here's the consequence, is that the R compound is going to rotate the plane polarized light 24 degrees in the opposite direction. And that's how you tell enantiomers apart, okay? If you're like, well, that's not easy. It's not. It really isn't, okay? You have to make a solution, you have to set up the polarimeter and everything, and then you measure it. But again, one's going to rotate plane polarized light in one direction by a certain amount, and the enantiomer is going to rotate the plane polarized light by the exact same amount, but in the opposite direction. Okay, that's how it works. Okay, so there's this specific rotation formula on here. I'm not going to ask you to do any calculations at all. Okay, I repeat. Okay, I'm recording this and I'm going to post it to the internet. Okay, that I will not ask you to do any calculations. However, I want to go through this with you. It says enantiomers are going to rotate plane polarized light to equal to degrees, but in opposite directions. One's going to rotate it positive or clockwise a certain number of degrees, and the enantiomer is going to rotate it in the exact same amount, but in the opposite direction. So it says here the degree to which the light is rotated depends on the sample concentration and the path length of the light. So it depends on the concentration. So the concentration is this C here, and the path length is this L here. So we have concentration and then the path length here. And so it says the standard optical rotation measurements are taken with 1 gram of compound and 1 milliliter of a solution with a path length of 1 decimeter for the light. And so when we report an optical rotation, okay, we have a number, which is a number of degrees, and we usually report the temperature and the wavelength of the light. So the wavelength of light, like I told you, is always the D line of sodium, which is which is around 598 nanometers, which is neither here nor there. So normally what we do is we do the reading at 20 degrees and with a D line of sodium. So I'll just tell you that the standard that we use is we put the optical rotation in here. I'll just put alpha because that's what we call it. Okay. The temperature is usually 20 degrees. So we just write 20 at the top. And then if you're wondering, well, wavelength, shouldn't you write 589? No, it wouldn't be that simple. The way chemists do it is they write D for the D line of sodium. But again, you will not be asked to do any calculations. Okay, so let me show you something that will hopefully help this crystallize in your brain. Okay, to compare these two enantiomers, you have R2-bromobutane and S2-bromobutane, right? Everybody here could name these compounds. You don't need my help, right? You know that the proton for the R compound is going in the back like this. So the bromine is number 1, the ethyl group is number 2, the methyl group is 3, and the hydrogen is number 4. So we go 1, 2, 3. That's clockwise. So yes, this is an R compound. So that looks good to me. Now it turns out that somebody went ahead and they measured the optical rotation, right? We call it the alpha or the alpha D sometimes. It just means optical rotation. So that's all the alpha means is optical rotation, meaning how much it rotates plane polarized light at 20 degrees. The light that we're using is the D line of sodium. It's the standard all across the world. And it's negative 23.1. Now, they didn't write degrees in here, but that's what it means. It's negative 23.1 degrees. And so if you put in S2-bromobutane, what's it going to do? It's going to rotate it positive 23.1 degrees. So it's the same amount, but it's opposite. So R and S in positive and negative, there's no correlation between the two, okay? So we'll put here no correlation. Trust me, I was a student taking this class, a long time, 30 years ago. And I certainly was like, oh man, I wanted to correlate these two. I was hoping that all our compounds would be positive and all S compounds would be negative. Well, there's no correlation between R and S and positive and negative. And if you're wondering, well, can you predict it? Is there a way that you could predict like how much it's going to rotate and whether it's going to be positive or negative? I got some bad news. The answer is no. You cannot predict it, okay? So we call positive rotation dextrorotatory, right? That's right-handed, and we call negative levorotatory. Now, if you look at this compound here, so this is aspartic acid, but if you look at this compound, it's an S compound. So if we put in the proton, it's in the back like this. So we have 1, 2, 3, 4, right? So it's going like this. So yes, this is an S compound, but check this out. Are you ready for one that's really going to blow your mind? Is that the compound is levorotatory, meaning it rotates the plane polarized light in the negative direction at 20 degrees Celsius. But then if you heat it up, it changes, okay? It goes to positive. So this is why we always record the temperature. This is why we say when you record the optical rotation alpha, you do it at a specific temperature and with a specific wavelength of light. So again, there's no correlation between R and S and positive and negative. It can't be, there's no correlation, and they also can't be predicted. So you can't predict whether the compound is going to rotate plane polarized light in the positive or negative direction. Again, I'm sorry, but that's just the way it is. So again, how do you get it? The only way you get optical rotation is by doing an experiment. Okay, that's the only way you do it. So you have to have what's called a polarimeter, and you have to make the solution, which is kind of a pain. Anyhow, but I digress. So it says here, we can predict the rotation of a racemic mixture. So racemic mixture means you have a 50-50 mixture of R and S. So R and S and the ratio is 1 to 1. Well, let's think about this. If they rotate plane polarized light to the same magnitude but in opposite directions, well, that means that if you have a 50-50 mixture, let's say one rotates at positive 10 degrees, the other one's going to be negative 10 degrees, and so they cancel each other out. And so if you have a mixture that's racemic, meaning 50-50 R and S, it doesn't rotate plane polarized light at all. Okay, it doesn't do anything, right? They cancel each other out. So yeah, you don't get a lot of information from that. However, and I'm not going to ask you about enantiomeric excess. I'm just going to kind of go over the definition with you. If you have, like, let's say more R and less S, like let's imagine you have, I don't know, 70% R and 30% S. We say that one enantiomer is present in excess, and the mixture is going to have some optical rotation, but not as pronounced as it would be if it was pure. And there's calculations you can do to figure out percent enantiomeric excess. But again, I'm not going to ask you to do a calculation like this. It's covered in the textbook, but I won't ask you to do it, okay? You just need to know that enantiomeric excess means that you have one, either R or S, more prevalent than the other. It doesn't mean anything more than that. So here's a summary of what you need to know, okay? So you need to understand what plane polarized light is and how a polarimeter works. That when you put a solution of the compound and you shine plane polarized light at it, if it isn't an R compound, it's going to rotate plane polarized light to one direction. The S compound will rotate it the same amount, but in the opposite direction. You can't predict whether it's going to be positive or negative. You will not have to calculate specific rotations. You will not have to calculate enantiomeric excesses, but you should know what is meant by optically pure. So optically pure just means it's pure R compound or it's pure S compound. Enantiomeric excess, all you need to know is that means you have more of R or more of S. It's not a 50-50 mixture. And then you need to know that racemic mixture means 50-50. So 50-50 or 1 to 1 R to S, and it's not optically active, right? It doesn't rotate plane polarized light whatsoever. All right, so I remember studying this and being kind of shocked and thinking that's all you have is you've got to do some kind of experiment to determine whether you've got an R compound or an S compound, and the answer is yes, you do. You actually have to get a polarimeter set up, got to purify the compound, and it is kind of it's time consuming, but it's one of those necessary things that we have to do as organic chemists. All right, so give me a thumbs up if you're with me on the idea of enantiomers, right? Enantiomers were non-superimposable mirror images. We could put here like human hands, right? the connectivity is the same, right? You have the thumb and the fingers organized in the same way on both hands, but they're mirror images and they're not superimposable, okay? So to take stereoisomers one step further, we can have another kind of stereoisomer that's called a diastereomer. And a diastereomer means they're stereoisomers, so the arrangement of the atoms in space is different, but they're not mirror images, okay? And you've actually seen examples of diastereomers already. The first one that we saw was cis and trans, right? Cis versus trans compounds. Okay, so let's say I have, this trans compound and I have this cis compound. Sorry for the poor drawing. But anyhow, those two compounds are different, right? They have a different arrangement of atoms in space, but they're not enantiomers. They're not mirror images. And so that would be one example of diastereomers. So there you go. You've already uncovered the definition, and you see it here. Okay, so cis and trans 2-butene. What's the definition? They're stereoisomers, right? But they're not enantiomers. And if it's if they're stereoisomers but they're not enantiomers, the answer is they are diastereomers. Okay, that's kind of the definition. Not kind of, that is the definition right there. Stereoisomers but not mirror images of each other. Answer is, what do you call them? They're diastereomers. Now, are these two compounds going to have the same physical properties? Absolutely not. Right? They have different shapes, different arrangement of their atoms in space, and so they're going to pack differently, and so they're going to have different boiling points, right? They're going to have different, we'll put here, physical properties. So they're going to have different boiling points, they're going to have different melting points, they're going to have different densities, etc. Okay, all their physical properties are going to be different, unlike enantiomers, which had the same physical properties. So besides diastereomers like cis and trans, we have to look at how R and S have to look at stereocenters or chiral centers, what they have to do with diastereomers. So there's a lot of information on here, but I think I'm pretty good at sorting it out for my students. So let's take a look at just the two compounds in the top left-hand corner, okay? If I compare these two compounds, would you say, and this is not me trying to fool you or tease you, would you say that these two compounds are enantiomers? You don't even have to look at the R and S, just look at the dashes and wedges. Are these enantiomers? Yes or no? Would these two compounds be enantiomers? Anybody? These two compounds are definitely enantiomers, right? How do we know they're enantiomers? They're enantiomers because every wedge was flipped to a dash. That's how we determine whether we have enantiomers or not. We flip a dash to a wedge and a wedge to a dash, right? So we see with these two compounds, okay, again, every single wedge is flipped to a dash. This wedge flipped to a dash, this wedge flipped to a dash. So that is the definition. So these two compounds are enantiomers. So we would say these are enantiomers, right? They're non-superimposable mirror images. If you were to take this compound, okay, another way, and rotate it 180 degrees, hopefully you can see that you would end up with the mirror image of this compound, okay? So these two compounds are enantiomers. Let's look at these two compounds here. Are these two compounds enantiomers? Yes or no? Would these two compounds be enantiomers? See, the wedge is flipped to a dash, the second wedge is flipped to a dash, the third dash is flipped to a wedge. Yes, so these two compounds are enantiomers. Good, great. Now, hopefully you can see the relationship between all these pairs of compounds. The one on the bottom left, you can see that every wedge is flipped to a dash, the one dash is flipped to a wedge. So these are enantiomers. I can't spell enantiomers. Enantiomers. All right, and then the last two are enantiomers as well. So what is in the green boxes is they're showing 4 pairs of enantiomers. Okay, so we have 4 pairs of enantiomers. Now what I want to do is this. If I circle this first compound in red, okay, if I circle this compound in red, and I compare it to this compound, okay, are those two compounds enantiomers? Are those two, the two that I have in the red circles? Are definitely not. Thanks, Isaac. No, not at all. right? You see that these two stereocenters, this one is the same, this one is the same. But this one is different. So what does that mean? That means that these two compounds are what? They're diastereomers, aren't they? Right? Because they're stereoisomers, but they're not enantiomers. So this compound and this compound are diastereomers. Okay? Well, it turns out that if you look at all the other compounds, that first compound is a diastereomer to this one, this one, this one, and this one. So the first compound that I circled, the first compound in red, what does it have? It's got one enantiomer and it has 6 diastereomers. Okay, so I'll scribble that over here. This compound has one enantiomer and it has 6 diastereomers on this page. Okay, and you could do that with any compound on here. Let's just pick one at random. We'll pick this one here. Okay, this compound that I have in this red circle, it does have an enantiomer, this compound right here. But if you look at its relationship to, I'll use a blue pen, to this one, this one, this one, this one, this one, this one, you see it's diastereomers to all of those. Give me a thumbs up if you're with me on the rationale here. That it's stereoisomers to all 6 of those compounds, but they're not enantiomers. Cool, okay? So there you go. So it says there are 3 total stereocenters in the compound. And so there's a total of 8 possible stereoisomers. Okay, so all 8 of these compounds are different. And so every single one of these compounds has one enantiomer, but they all have 6 diastereomers, right? Which makes a total of 8 compounds. So how do you know when you have diastereomers? Not only can you look at the dashes and wedges, it's actually easier to look at the RNS, okay? So you can see that somebody did all the work for us here, and they told you which that the stereocenters are R or S. So what you can do is this. You look at this R has been flipped to an S, okay? This R has been flipped to an S. So far, it's looking like enantiomers, and this R has been flipped to an S. So we see that all of the R's have been flipped to S's, so therefore we don't even have to look at the structure. We can just tell that they are enantiomers, all right? So what if I compare these two compounds? I can see that this R, that the third stereocenter is an R, the second stereocenter is an S, and that the first stereocenter is flipped as well. So one of them is identical, but the other two are flipped. So what does that tell you? That these compounds are not enantiomers, but they are stereoisomers. So again, you don't even have to see the structure. All you have to do is look at the RNSs. If they're all flipped, it's an enantiomer. If some of them are flipped and some of them aren't, it's a diastereomer. End of story. Okay, so you don't even have to have the picture to figure that out. All right, so if you're wondering, well, when you had 3 stereocenters, how did you know that there was a total of 8 stereoisomers? Well, you can actually use a formula to determine that. So it says here, with the number of possible stereoisomers for a compound depends on the number of chirality centers in a compound. So what does that mean? If you have 3 chirality centers, you use this or any number of chirality centers, you use this formula, 2 to the power of n, where n is the number of chiral centers. So if we go back to this page here, we say 2 to the power of 3 stereocenters, so that gives you 8, okay? So let's say you had cholesterol. Well, how many? Oh man, there's all kinds of chiral centers in cholesterol. If I just circle them all here, I'll use a red pen. I have one here. I have one here. There's another one here. There's 3, 4. Let's see, 5. There's one here. 6, 7. I think I'm missing one. Oh yeah, down here there's 8. Okay, so there's 8 stereocenters for cholesterol, and so if we take 2 to the power of 8, we actually end up with 256 possible stereoisomers. Is that wild or what? With 8 chiral centers, there's 256 possibilities, but your body is smart enough to make this one stereoisomer every single time. So it's pretty remarkable. So now what we're going to do is we're going to look at pairs of compounds and we're going to figure out whether they are enantiomers or diastereomers, okay? The first two are pretty quick. If I look at A, so in A, without too much thinking, could anybody tell me, would these two compounds be enantiomers or diastereomers? And there's no trick questions. There's no trying to fool you or tease you. Yeah, thanks, Jennifer. Yep, they're enantiomers. Can't argue with that, right? This wedge is flipped to a dash. This dash is flipped to a wedge, so absolutely. Perfect. So we'll put here enantiomers. Jennifer, do you have the answer to the next one? Or anybody? Yep. Thanks. Yeah, the next two are diastereomers, aren't they, right? You can clearly see that one of the wedges is flipped to a dash, the other one remains unchanged. So they're stereoisomers, but they're not enantiomers, therefore they are diastereomers. So diastereomers. The next one, it requires a little more work, doesn't it? Right? Because they didn't put the molecules in the same orientation, right? They put this chlorine here in the plane, but down here it's on a wedge. So there's two possibilities here, okay? There's two ways to solve C. Number one is you could just figure out the R and the S of every single stereocenter, and then you could compare them. Okay, if both stereocenters are flipped, then they're enantiomers. If only one of them is flipped, then they're diastereomers. Or you could rotate one of the bonds. You could, so if you're really good at manipulating molecules, you could rotate this so that you get the methyl in the plane. So if I get the methyl in the plane, so I'll just do this for you. So if I rotate this compound so that I get the methyl in the plane, what you end up with is you got your methyl in the plane like that. The hydroxyl is still going to be out here like this. But keep in mind that since the methyl is coming out, to put the methyl in the plane, I only have to rotate it 120 degrees. Okay, and so that means that the chlorine would be going in the back like this. Okay, if you need to use a model, if you have to, okay, I don't have to, and not that I'm that great at it, but if you look at the relationship now, you can see that this chiral center is identical, but this one has been flipped. The one in green has been flipped, so you can see that the relationship is diastereomers. So I'll just scribble that down here. These are diastereomers. However, if you don't like that, if you're like, I don't think I'd do that, Mr. Dion, well, what we can do is we can just evaluate the chirality at every chiral center. So let's do it, but we'll go a little quick, a little faster than we normally do. So for this chiral center here, the oxygen is going to be number 1. The proton is in the back. I'm not even going to draw it. This will be 2. This will be 3. So we go 1, 2, 3. It's going clockwise, and so this would be an R stereocenter. So we'll scribble that in here. This one is R. For the next one, we have 1, 2, and 3. The proton is in the back, so this is going to be an R stereocenter as well. So we've got R, R. All right. For the next one, you can see that this is definitely an R again. And then if we look at the last one, the proton is in the back. Okay. We have 1, we have 2, we have 3, and so it's going like this. So that is counterclockwise, and so that is an S stereocenter. Okay, so I'll scribble that down here. This is an S stereocenter. So again, you can clearly see that they are enantiomers. Let me find the question again, now that I lost it. Okay, so what did I say? We said that these two are enantiomers. We said these two are diastereomers. This is an R stereocenter. This is R, and this is S. And so these are diastereomers as well. But again, either treatment works. Okay, either way is going to work. I'll just tell you right now that ACS and MCAT, they love this kind of question. This is kind of like ACS or MCAT kind of material. Why? Because it asks you more than one thing in the same problem, right? You have to know what the definition of diastereomer and enantiomer is, but then you've also either got to be able to assign R and S, or you've got to be able to rotate the bond, as I had shown before. Okay, either way works, but they love those kind of questions where you ask two things at the same time. All right, so there we go. Any questions about that one? Enantiomers or diastereomers? Okay. Well, it's only 8:44 in the morning. I want to show you a couple more things before we take our first break, okay? So we're going to move on to section 5.6, which deals with symmetry and chirality. And I've been teaching chemistry for long enough to know that students are usually very, very adept, very good at recognizing symmetry in a molecule, right? If I was to ask you to find symmetry in this molecule, every single person would say, well, you just draw a line down here, right? Because if you draw that compound, right, it's just this, okay? So this compound, so you could just draw a line down it like that, and students would, find that so quickly, it would make my head spin, okay? But with this one here, it's not quite as abundantly clear. Okay, there is symmetry in this compound, but there's not symmetry here, right? That's not a line of symmetry. It's more here. If you were to rotate this compound, okay, if you were to rotate that compound 180 degrees, it would be identical. So there is rotational symmetry in this compound. Anyhow, let's take a look at what it says here in the slide. It says any compound with only one chiral center or one chirality center is going to be a chiral compound. So that's just the definition. If you've got one chiral center, your compound is chiral. End of story. So you might be thinking, oh boy, where is he going with this? Because that what he's trying to say is that if you have more than one chirality center, the compound might not be chiral. The answer is yeah, absolutely. Okay. So check this out. If you have two chiral centers, sometimes the compound may not be chiral overall. So what does that mean? It means that even though you have chiral centers in the molecule, if you put it in a polarimeter, that instrument that you shine the light on and everything, it doesn't rotate the light at all. And if you're thinking, well, why the heck would it do that? Okay. Well, let me explain it, but let's take a look at this again. So you can see that in both of these compounds, trans 1,2-dimethylcyclohexane and cis 1,2-dimethylcyclohexane, you can see that we have a chiral center here and here, and then we also have a chiral center here and here, okay? So we can totally see that there's two chiral centers in the compounds. However, it turns out that one of them will rotate plane polarized light, but the other one won't. And let me tell you which one it is, okay? It says the trans isomer is chiral. Okay, so this is a chiral compound. That means it rotates plane polarized light. This compound is achiral. So if you take this compound, and you can't argue with this, this is a stereocenter. I can't argue with that's a stereocenter, but it doesn't rotate plane polarized light. Now, if you're going, what gives? Okay, why would that be? Well, there's a very good reason, okay? Because if the molecule has a plane of symmetry, right? This had symmetry, but it wasn't a plane. It was an axis, right? It was a dot that you could rotate it around. That's an axis of symmetry. This compound has a plane of symmetry running right through it. So if your compound has chiral centers in it, but it has a plane of symmetry, it doesn't rotate plane polarized light. So check this out. It says the cis isomer has a plane of symmetry, which means it's superimposable on its mirror image. And so what that means is that even though, and I agree with you, even though it has chiral centers in it, it's not a chiral compound. Another way to think about it is like this. So let me just sneeze, and then I will take a look at this compound with you in more detail, okay? So if we take a look at this compound here, we have a hydrogen going down here, and we have a hydrogen going down here. Now, it might be difficult for you to do this, to orient yourself or to imagine yourself looking down on this bond. But if I look down on that bond, I would give this carbon priority 1, this one 2, and the methyl would be 3. So I'd be going 1 to 2 to 3, which would be counterclockwise. So this would be an S stereocenter. And again, if you have to make a model of this to prove it to yourself, it's totally fine, okay? So that is an S stereocenter. But if we do it with the other chiral carbon, so if we take our eyeball and we move it over here and we look down here where the hydrogen's in the back, so let me just erase this here, then this carbon is going to be number 1. This one would be 2. This one would be 3. The hydrogen is obviously going to be number 4. So if I'm looking down there, I'm going to go from 1 to 2 to 3, which is going to be clockwise. So that means that this chiral center is an R chiral center. So what does that mean? It's almost like you've got a racemic mixture in a compound in a way. Now, that's not the way you describe it, okay? That's just me teaching it to you. It's not proper what I'm saying. But the idea is this. If you have one chiral center that rotates plane polarized light in one direction by a certain amount, then you have the exact same type of chiral center in the same molecule rotating plane polarized light by an equal amount, but in the opposite direction. What do? The two chiral centers cancel each other out. And so it doesn't rotate plane polarized light. And we have a special name for that kind of compound. So when you have a molecule with an even number of chiral centers and it's got a plane of symmetry, we call it a meso compound. So this is not like miso soup, that's M-I-S-O, but meso compound. And a meso compound is a compound that's going to be identical to its mirror image. So that's one way to test for a meso compound. What I have found, though, is that students usually don't have to draw the mirror image of the meso compound. They usually don't. Okay, usually what they're very good at is recognizing a plane of symmetry. I would say 99% of the time, my students just find a plane of symmetry and they say, well, there's symmetry in the compound, therefore it's, even though it's got chiral centers, so therefore it's meso. The whole idea of drawing the mirror image, you can do that, okay? It's useful, but again, I've taught the class a lot, enough to know that I don't see students doing that very often. Students are usually excellent at recognizing symmetry in a molecule. So it says here, if a compound is a plane of symmetry, it is achiral. So if we take a look at these two compounds in this green box here, I'll just zoom in on it, okay? We've got two chiral centers, okay? We've got a chiral center here, we got a chiral center here. So the total number of stereoisomers should be 2 to the power of 2, which would give you 4. Now you can see that this is a pair of enantiomers, right? Because this wedge has been flipped to a dash, this dash has been flipped to a wedge. There's no arguing over here. But then if I look at this compound, okay, where I have two edges, you can see that these two compounds are identical, right? If I rotate this one 180 degrees, I end up with the same compound. So what does that mean? It means that when you use this formula, 2 to the power of n, it means that when you punch the number of stereocenters in there, it gives you the maximum possible number of stereoisomers. If you have a meso compound in there, it means you're going to have less than the predicted number of stereoisomers, right? So in this case, there are not 4 stereoisomers. There's actually 3, right? Because one of them is a meso compound, and these two compounds are identical. And so there you go. That's it. So if you're wondering, oh man, are you going to give me like 30 stereoisomers and then I have to root through them and find a meso compound? Of course not. Of course not. I'm only going to ask you something that is very manageable. And we're going to take a look at an example of a problem like that in just a second. So right here, so it says draw all possible stereoisomers for each of the following compounds. Each possible stereoisomer should only be drawn once. So let's take a look at A. Let's take a look at A. So in A, we have 2 stereocenters. There's one here, there's one here. So if I use the formula, I would say 2 to the power of 2, which would give you 4. So that means there's a maximum of 4. There might be less, but there's a maximum of 4. So let's start drawing a cyclohexane like this. No, not like that. And we'll put a wedge, or sorry, a dash here for this methyl like this, and then we'll put a wedge for this methyl here, and then we'll flip it. Okay, so I'm just going to copy and paste it, and then we'll flip the wedge to a dash and the dash to a wedge, and that way we'll have a pair of enantiomers. So let me erase that, and I'll erase this, and so we'll put in a wedge up here. So there's our wedge, and then we'll put a dash going down here. So this is a pair of enantiomers. So what's my other possibility? I have a possibility where I could have 2, or I could have 2 wedges, or I could have 2 dashes. So what I'll do is I'll draw 2 wedges. So I'll put one like this and one like this. So there you go. Those are three stereoisomers. Okay, there's nothing wrong with any of those. However, what would happen if I was to draw a 4th stereoisomer, okay, and I put 2 dashes? Is this a new stereoisomer, this one that I'm drawing here? Is this a new stereoisomer? Could anybody answer that? What I just drew, is that a new stereoisomer? Is that brand new? No. Thanks, Jenny. No, absolutely not, is it? Right, because these two compounds are identical. Okay, these two compounds are the exact same compound. I just drew it twice. How do we know that? Because there's a plane of symmetry in the molecule, and therefore this is a meso compound. So I'm going to cross this one out because I didn't have to draw it. So that means there's a total of 3 possible stereoisomers for this compound. So what we're going to do now is we're going to take a short break, and I want you to try this one. Okay, I'm sure that a lot of you just figured it out in your head already without my help, but I'd like you to give it a shot. Like, try drawing out the different stereoisomers and see if you get the right ones. And then after that, all we have to do is finish the section on Fisher projection. So I'll tell you how to read RNS on a Fisher projection. And then after that, we're going to look at conformationally mobile compounds just for a second, and then that finishes the chapter. Okay, so that won't take very long. And once we're finished that, we're going to take a look at some more practice problems. So what I'm going to do is remind you that if you go into the chapter 5 module, you'll see that there are some problems, and it's called it just says chapter 5 practice problems summer 2024. Okay, so once we finish up the chapter, we're going to take a look at those as well.